Okay, so in this example, we're going to show that not all ideals are principal, namely this ideal generated by the constant polynomial 2 and the constant polynomial x in z adjoint x is not principal. Okay, so we show that this is not principal. Dang. Principal. So we can't be generated by a single element. So that is, there does not exist some f in z adjoint x such that the ideal generated by 2 and x is the same as the ideal generated by f. We're going to show no such f exists, and so it cannot be principal. Let's take a moment before we do that to think about what this set is to begin with. So 2x is a collection of all 2 times a polynomial plus x times some other polynomial, where p and q are in z adjoint x. And if we were to write out, I'm gonna quit clarifying where the coefficients and stuff lie. I think it should be clear from context. If we write out what a random, in fact, let's not even put it in set notation. If we write out what a random element of this looks like, we're going to get 2 times a0 plus a1x plus some power plus x times b0 plus b1x plus some other power. And so we're going to get as the constant term 2a0, but then as the linear term, we're going to get 2a1x and b0x. So that's 2a1 plus b0. And then for the quadratic term, we are going to get 2a2, but then we're going to get a b1, and so on. And this is going to stop at some point, plus some unknown constant I'm going to call star to some unknown power I'm going to call box. It doesn't matter where it ends, where it ends and what the coefficient is. And then I want to observe something here. Irrelevant of what p and q are, the constant term of an element of this ideal generated by 2 and x, this is always going to be even. Even if a0 is 0, this will always be even. The constant term of polynomials here is always, always, always even. Now, although for the next terms, although 2a1 is even, we're adding on b0. So we can effectively do something like set b0 to be negative 2a1 plus c, and we can pick whatever c we want here because we can pick whatever b0 we want. And so this is just going to become some constant c. In fact, I'm going to call it c1. And we can continue doing that, and we'll get some c2 x squared and so on. C whatever, c star, x to a whatever power. So my point here is just this. It's that elements here are polynomials with even constant term, and it doesn't matter what happens, like anything can happen after that. But if we were to more descriptively define this set, these are the polynomials with integral coefficients with even constant term. Okay, so that's what that set is. So now that we have an understanding of that set, we've settled into the problem. Let's now look and show that it cannot possibly be principally generated. So suppose that for a contradiction, suppose it is. There exists some, f in z adjoint x such that 2x equals the ideal generated by 2 and x is the same as the ideal generated by f. Well, what do we know? We know that 2 is equal to 2 times 1 plus x times 0. and that's in 2x. In fact, the generators of any ideal generated by any number of elements are always in in the ideal. It would be kind of silly if they weren't, right? So 2 is there, and since this ideal is equal to the ideal generated by f, there must exist some polynomial g such that we can write 2 as a multiple of f, right? Because 2 is therefore also in this ideal generated by f because they're the same, so 2 is some multiple of f. Well, let's take degree. So the degree of 2, on the one hand, is 0. On the other hand, it's the degree of f plus the degree of g. So what does that tell us? It tells us that the degree of f has to be 0. So f must be a constant. Okay, so f is a constant. Great. Right. So f is a constant. Also g is. So we have a factoring actually not in z adjoint x. It's a factoring in z because everything here is they're just constant polynomials. So this tells us then that f is either plus or minus 2 or plus or minus 1. Because those are the only factors of 2, right? Okay, but f cannot be plus or minus 1 because then this ideal has a unit. It has plus or minus 1, and so it's everything. But the ideal generated by 2 and x is not everything because we only get polynomials that have an even constant term. So for example, the polynomial 1 is not in the ideal generated by 2 and x. So f cannot be plus or minus 1. Thus, it must be that f is plus or minus 2. One of them. It doesn't matter which one because we have an ideal. It's closed under multiplication. We can multiply by negative to get one of the others. But can that happen? Well, what's the ideal generated by plus or minus 2? It's the collection of all. I'm just going to do plus 2 because this is irritating me. They're the same thing. It's a collection of all polynomial multiples of 2. Well, what is this? If you multiply a polynomial by 2, all of the coefficients are now even. So this is a collection of all polynomials over z with even coefficients. Does every polynomial in the ideal generated by 2 and x have an even coefficient? No. We could pick the other non-constant coefficients to be whatever we want. They don't have to be even. So as a specific example, x is not in 2 because its coefficient is 1, which is not even, but x is certainly in here. So what do we have? Well, we have that in this case, f also cannot be equal to 2, the ideal generated by 2 and x, and this is the end. So we conclude then that no f exists, and the ideal generated by 2 and x is not principal. So it's an honestly new ideal. And this is there's a whole theory about how you can sort of find non-principally generated ideals, and it's beyond the scope of this class. It's the subject of a topics course, but this idea, together with some of the stuff we're going to learn in the coming sections, leads you to sort of the idea of dimension in algebra, and a lot of cool stuff comes from this. But anyways, this is an example of an ideal which is not principally generated, and you'll do more examples in class in the group work.